Hi folks, this is the second video segment that I'm doing on showing you how to use a base excitation or restraint excitation functionalities in the Catia V5 in order to perform a single degree of freedom damped vibration model in that program. The very first example that I did, which involved base excitation or restraint excitation, dealt with the water tower that I modeled. Here, let's think about a single-story, single-bay building, such as what is shown here, where the ground is subject to an base excitation involving acceleration. This is the kind of thing that arises in earthquake engineering. So the data that is given here is going to be used to perform the calculation, and the objective is to plot the relative displacement of the floor, relative velocity of the floor, and the absolute acceleration of the floor in the problem. Now, this is to be done over a 3-second interval with zero initial condition. And in order to do this, obviously, we need to describe a modulation which describes the acceleration of the base. So I need a uh, Excel spreadsheet with this data, which represents this step function. Okay, so when you take the vertical axis is unitless, and the horizontal axis in second. So if you take this unitless values, the height, the amplitude, multiply it by g, which is 386, describes the acceleration of the base. Okay, now this is an example that's taken from Tedesco's book, and these are the plots generated by Tedesco using its homebrewed uh, differential equation solver for single degree of freedom system. Now, here is the relative displacement, relative velocity, and this is the absolute acceleration of the floor. Now, although we are not using the force excitation, we are not doing anything with force. If you take the acceleration of the base and multiply it by the mass of that floor, what you get is the effective force. So in a sense, although we are not inputting, we are not specifying the force information. If you take the acceleration of the base of the ground multiplied by the mass of the floor, you get essentially the force that is being acted on the floor. I'm going to be using or I'm going to be using spring rigid functionality to create the spring in the problem. Okay, so let's go to Catia, start with the part file. I will create 2 points, 1 point at 0, 0, 0. The other one is roughly 2.5 inches away, 2.5 inches away. Now remember, if you watch the videos that I did on modeling single degree of freedom problems in Catia, you'll notice that we do have to go through this motion. I have to create a line, I have to measure between elements, etc. But those elements are not going to be participating in the calculation. Unfortunately, that's the way it's to be done in Catia, and this is why I'm calling this playlist as killing of a fly with a cannon. Okay, because Catia's FEA capability is really not intended for a very basic elementary problem like that. Okay, so line going between this point and that point. Let's apply material to this thing. Apply material. We're going to apply dummy material aluminum. And I say dummy because I will change the properties of the aluminum so that essentially there is no stiffness and uh, there's no density, pretty much. So if you double click on aluminum, select the analysis tab, I'm going to make the Young's module of aluminum 0.1 psi. That's ridiculous because it's 10 million psi. I'm making it 0.1, and the density of it I'm going to make it 0.1. Hang in there. Let me just check what the density was. Let me cancel that. Try it one more time. I want to see what the value of the density was. So analysis. This I made 0.1. Now this density is already very small, so you know I'm going to make it even smaller. I'm going to make it -8, whatever it was, because this is in unit of a slinch per inch cube. I'm going to make it -8, so it's essentially 4,000 times smaller, or 10,000 times smaller. That's fine. Good. So we're done here. We're going to go to the generative structure analysis. We're not going to do static analysis. Frequency analysis is what we want. And restraints. Before I do the restraints, first I have to mesh this part, okay? So mesh it with beam elements right there. I use a minimal mesh, which means a single element from here to here. And then the cross-section of the beam, 1D property on that. Now, the size of this, the shape of it, and the number of elements in this along this line is not going to be used in the calculations, okay? Is not going to have an impact on the calculation. Let me put it this way, because remember, I took the Young's modulus of aluminum from 10,000 psi, I made it 0.1 psi. I'm sorry, from 10 million psi, I made it 0.1 psi. And that density of it, I made it 10,000 times smaller. So you'll have no effect. Now, the other thing is that let's actually create our analysis connections. Now, I don't want to put it between no point and point. I'm going to hide these points. So the first component is that vertex. The second component is this other vertex. So we created our analysis connection right there. And to specify the spring properties, I'm going to go to distant connection property. This last one, it says user defined. You click on it. You select that connection. You see that connection that you created? The only thing you can select is actually that connection. That's pretty much it. And then as soon as you do that, these rigids on the sides are dimmed. It really doesn't matter. So you click on the wrench, and for the stiffness in the y direction is 100,000 psi. Right? Not psi. Sorry, 100,000 pound per inch. That's what I meant. Close it. Now let's put a mass here. So lumped masses, right there, see that? Or distributed mass, lumped mass at that point. Now this number is going to be your 50,000 divided by 386. That is the mass. Okay, it's 129, this unit, slinches. And the 50,000 came from 50,000 divided by 386. Okay, good. You say okay. Now, if I the restraint. So this end is clamped. So here on my restraint, you can see that. Clamp this end. And this end can only move in the y direction. So user defined, you click on that. Can only move in the direction y, direction 2. Now, if I run this thing, that's pretty much it. If I run this thing, I'm going to get an error message. You'll see what the error message is. It says, hey, this is a single degree of freedom system. You're asking for 10 frequencies. And that is correct. So unfortunately, I have to go to this frequency case. Instead of 10, ask for 1. Good. Let's run it again. There won't be a problem. Done. So you go to sensor frequency, double click on the frequency list. You get 4.422 hertz. Now, if you use the elementary formula, omega equal to square root of k over m, natural frequency equal to square root of k over m, put the right k and right m, you're going to get this number times 2 pi, because that formula is going to give you radians per second. So convert that number to hertz, you divide it by 2 pi, you're going to get exactly this number. Good. Now for the rest of the problem, I'm going to insert transient dynamic response. You click on it. It says, what is your frequency case solution? Well, it's right here. We just did it, right? You have to select it, and it goes in that box right there. And it's not a load excitation. It is restraint excitation. Say, okay, good. A couple of things. I don't want to do the analysis over 10-second interval because default is 10 seconds. I want to do it over 3 seconds. That's what this thing said, over a 3-second interval. Okay. Damping is going to be, you double click on it, select the range. This is going to be 12%. And that is your 0.12. Okay, good. Restraints, well, X and Z coordinates don't matter. They don't participate. This is a single degree of freedom in the Y direction. So you select the second row. And for the multiplier is going to be this G, 386. Okay. You put the 386. Okay. And it says, where is your modulation? Well, the modulation is that Excel spreadsheet that I have already created. I have to read that into the program or import it. I don't have to cancel this thing. I can say OK and come back and select the modulation later on. Say OK. Good. So now we go to this, where is that toolbar? This is modulation right there, modulation. And not the frequency one, the T, time. You click on it, browse. There is my folder fooling around. So here's the basic excitation, single story, single bay. Say OK. And we can always check it. If you see that there's this branch of modulation, put the cursor on time modulation, right click, generate 2D display, and this is going to be the plot that we had here. Okay, good. You can close that. And that's pretty much it. That's pretty much it. So you put the cursor there, right click, generate 2D display, next, finish. Now notice that when you select the layout, displacement is being plotted. So let me go ahead and select that point because it says go pick the point. Now I'm going to hide this. I'm going to hide that. And I'm going to select this endpoint, which is node number 1. I don't want anything about X and Z, so I just want TY, translation Y direction, and say OK. So this has been generated, but you double click on it, and it says, in there. I think I must have missed something here. Let me see for a second. Double click. Let me go and select that again. I don't want X and Z. Well, that's already selected. And it's a displacement. Very good. So double click on this. Okay, so you double click on this. And you're going to get this graph. And you say, what the heck is this? Now, you can plot other stuff too, but it doesn't matter. They all look weird. Okay. Good. So the problem is that what we are plotting here is the absolute the data. Okay, I don't want absolute data. I want relative displacement and relative velocity. So this is kind of useless. I'm going to delete this. So now I go and do the following: put the cursor on sensor, right click, create local sensors. Now what do we want? We want relative displacement. That's one. Let's go down here. We want relative, with the control, relative velocity there, and acceleration. Acceleration is just a global acceleration. You say, okay. So notice that they have been created. Displacement, acceleration, velocity. Okay, good. So let's start with the displacement. Double click on it. It says, what is the support? The support is this endpoint. You say, okay, let's do the same thing with the other one. Double click. Where's the support? It's this endpoint. Let's do the other one. Support is this endpoint. You say, okay. Let's start with the displacement. First of all, this requires updating, and let's see now, updating, you can do it from here, update sensors, and now you double click on this. Oops, not that, don't double click on it. Put the cursor there, right click, generate 2D display, and there we are. The problem is that this is very jagged, and it has to do with the fact that when I did the transient dynamic response case solution, I left this number of steps as it is. Let me make this thing 200. The way it works, you start with something, for example, default. You get a graph. You go make it 200. Look at the graph. Has it changed a lot? If the answer is yes, then maybe you have to go and select even more. And then check again until a point where things don't change that much. So just for the heck of it, I'm going to make it 1,000. I'm not going to do it in several steps. I'm just going to make it big number of steps, 1,000. And now put the cursor there. Well, first of all, update and right click, generate display. Actually, this is already done. It's already there. I don't have to do that. Just double click on it. There we are. Now you might say, "Oh, what is this?" Well, that is displacement, except that it's in meters. Well, just look, meters. So put the cursor in the white area, right click, options, not meters, MKS, but define options, which was in inches, obviously. Aha. And now this is that, right? Except that it's flipped. That's okay because the 386 that you put in there, it could have been minus 386. You don't know which one kind of the ground is moving. So let me do the following. To make it look exactly like that, let me go to the restraint excitation here. Instead of this thing, instead of plus 386, I make it a minus 386. Whatever we got is correct. It's just that it doesn't look good. That's all. Double click on it. And this now looks like that guy on the top. Okay. Numbers, notice that start at 0 goes to 0.2. Do we have the same thing? Yeah, 0 to 0.2. If you don't want to see this guy in the middle, it's blocking your, obstructing your view, you put the cursor there under options, title, top left. No. I want the, for example, top center. How about that? There. At least I can see what's going on. And then this, of course, goes to roughly minus, what's this peak down here? It's minus 0.3. Is that what you got? Yeah, minus 0.3. Very good. Very good. Now, if we go to this plot, okay, we close that. Down here, right click, update sensor. This is acceleration. This is the global acceleration, absolute acceleration. Right click to the geometry, 2D, not geometry, 2D display, and the unit is not meter per second square. Put the cursor there, right click, options, not MKS, inch per second squared. Now this is that. Well, let's check it out. 100, check it. Yeah, we're going to come and fix this thing. This is not wrong. Let me go to velocity first, and then we come back and look at this. This is not wrong. It's just that it's a different situation. So we go here, right there, right click, update sensor, right click, generate 2D display, and this is that velocity, relative velocity. So it goes to roughly 3 inches, and then peak here -6. A unit, I have to fix the unit. Right click, option, yeah, 2 -6-ish, etc. Now, yeah, -6, and then you can see that that matches this kind of plot. Now the question is, what's going on here? This is absolute, I want absolute velocity, right? So let's go ahead and figure out what is it that we, this one, acceleration vector. Let me delete this. Let me delete this. Let's go and do another one. Sensor, create local sensor. Let's read this thing carefully. Let me see for a second. Go down here. Relative velocity, velocity vector, acceleration vector. Uh, let me try relative acceleration vector. Let me see how different that's going to be. Double click, select that, update sensor, generate 2D plot. Change the unit, options, appropriate units. Yeah. So this, actually what we wanted to do, this is a mistake. This should be relative. This should be relative. Yeah. Relative. Relative. Yeah. Relative acceleration vector. Now, if you want the absolute acceleration vector, then here's what you do. Just make sure that this is correct. Yeah, that's this, 100, and then the other peak is also around 100-ish. Yeah, good. So let me close that. If you want the global one or absolute one, you put the cursor there, right click, create local sensor. Down here is acceleration vector, not the relative one. You say OK. Once again, you double click, you select that, and you say OK. Right click, update sensor, and then generate 2D plot. And this is the absolute acceleration vector. Yeah, so anyway, there is no issue with these. We reproduce these things. It's just that this was a plot of relative acceleration vector. Good. That's pretty much it. Good luck. I want to do one more example of base excitation where we have a car going over a rough road where the road is going to be modeled as a sinusoid. Okay, we'll do that. That's going to be the third example.